day 4, video 3 at least. We're going to look at this other kind of form, which we're going to call modulus argument form. IB calls it polar, which is annoying because our calculator calls some other form, which we also have to learn polar. So there's a lot of like shifting around between different notational names and knowing like, oh, my calculator calls it this, but my IB test is going to call it this. But it's not, the ideas themselves flow pretty easily between. And once you know what you're looking for, it'll be really clear which form is which form. So a lot of the time the kids will call this modulus argument form, they call it CIS form, CIS right here. So that would be one way you could sort of articulate which one of these ones you're talking about or thinking about. So we're going to be thinking about what IB calls polar, what we're going to call CIS forms, which is a funny name, haha. But it's not, again, a lot of new content. It's just putting together old ideas in a new way. So that can be kind of helpful. So modulus argument / polar / CIS form is basically thinking about what a point is at in terms of its angle and its magnitude instead of thinking about it as like a coordinate. So if you were thinking about this point right here, right, the x coordinate would be this long, the y coordinate would be this long. So if you wanted to take this point right here and turn it into our regular Cartesian form, what we've been studying up to this point, you would say, oh, this is root 3 over 2 plus 1/2 I, if you wanted to think about it as a complex number instead of as a point on the xy plane. Okay. So then let's think about that point in a little bit more detail. So if you were to go into your calculator and do tangent inverse of 1/2 over root 3 over 2, that would produce an angle of 30 degrees or pi over 6 radians. Okay, pi over 6 radians. Push that up a little. And then when you think about this length right here, we could do that side length, c squared is equal to 1/2 squared plus root 3 over 2 squared, and that's going to give you 1 equals c squared, and so c is 1, which makes sense because, you know, it's the unit circle. So 1. So if you wanted to think about this point right here, if you wanted to convey to a reader or someone who is interested in what you were looking at or talking about, a couple of ways you could do that. You could talk about it in xy coordinate plane. You could talk about it as a complex number, which we looked at as root 3 over 2 plus 1/2 I, or it conveys the same information to say convey location if we just tell them the modulus and the argument. Because if you know how far to turn and you know how long it is, then there's really only one place that could be. So that's kind of what this modulus argument form is. It says that the x component is going to be found, can be found by taking, let's say this is 1. We have opposite here and adjacent here, never forgetting our little friends. So the x value is the adjacent side over 1, because this is the cosine of the angle. So cosine of that angle equals adjacent over hypotenuse. Hypotenuse happens to be 1. So the x value can be thought of as the cosine. And then the y value is the opposite over 1, which is the same as the sine of theta. Okay? Now put these together with this up here. So root 3 over 2 is that part. So root 3 over 2 is the same as the cosine of, in this case, 30 or pi over 6. And 1/2 is the same as the sine of theta, in this case 30/pi/6. So that would be one way you could convey this location. You'd say, oh, this is the x and this is the y. But when we talk about complex numbers, we build it as the x is the a component plus the y, which becomes the bi. So instead we say the cosine of pi/6 plus the sine of pi/6 times I, because this is the same as √3/2, and this is the same as 1/2, and then I. So those two are going to go together. If, for instance, this weren't 1, you would have to do something a little different, right? Because this is going to only give us if it's 1, right? So in this case, it works cleanly, but it won't always work that way. You might have to scale this up by 5 or 10 or however long it is, but we'll look at that. So that's kind of the building block to this idea. So this then right here gets rewritten one more time as cosine pi/6 plus, let's throw that I in front, sine of pi/6. And look, now you have CIS. So that's where this cis pi/6 comes from. So it's kind of the building blocks for this cis form. Then if you have one that isn't one long, so if you had one that was like, let's say this is 3, and I'm going to make this very difficult for myself, theta, we'll just leave it as theta. So the x/3 is going to be the same as the cosine of theta. So then 3 cosine theta is x. And sine of theta is going to be y/3. So 3 sine theta equals y. So now we want y instead of being y. And instead of thinking of this as x comma y, we're going to think of it as a plus bi, where a is the x, b is the y. This becomes 3 cosine theta plus 3 sine theta I. Let's factor that 3 out. Becomes 3 cosine theta plus I sine theta. And then there it is, 3 cis theta. So that's that notation. So what you'll see always with this modulus argument form is that whatever the length r is becomes that leading term here. So 3 or 12 or whatever the case may be is going to be the modulus of the number. And so you could say your complex number z can be written as r being the magnitude, cis theta, where theta is always going to be in radian mode. So we're going to use technology instead to do this, to help us be able to figure out. You could go back and do it by hand. We already happen to know, because this would be a 3, 4, 5, right? 5, 3, 4. So 5, and then we would need this angle right here, 5 cis, and then you would be looking for the angle. So let's go find that, use our calculator to help us do that. So let's do angle, and let's just go in and edit this so our lives are a little easier. Plus 4i, and it gives us 0.927 as our radian amount, which is pretty messy, but that's fine. It doesn't matter. It doesn't need to be clean. If we hadn't known, we could also go menu, number, complex number tools, and we could go magnitude. And you would just do 3 plus 4, always irritating, I, and you would get 5, which we knew because it's a 3, 4, 5. But let's do one that's less friendly. So this one is, let's come up here and we'll just copy and paste. Oh no, I lied. let's see, it's a lot of messy. So negative, making sure to use the negative symbol and not the minus symbol. Square root 15, come outside the square root, plus I times, just to be sure, because you never know, these things can be fussy, root 15, and hit enter, and it tells us that the modulus, this modulus is 5.4. Let's just do 8, and then we're going to say cis, and we'll put down the angle. Let's do angle. And we're going to delete all this. Let's see if we can copy and paste and do a little finagling in here. No, maybe? No, that's annoying. So again, I'm going to do 15 to the 0.5 because that's way easier, plus I, and then 15 times 15 to the 0.5 because that's the same as the square root. And I need to go back in here and make this negative, and there it is. Oh, so you can see how the roots become sort of a pain, particularly on the computer. 3.4, 3.56, 3.56. So that's our angle right there. So that would be how you would convert this particular one into cis form. Okay. If you have a situation where you have the other way, right, like this one down here, it actually is hopefully friendlier than we think because we can just go 3 and then cosine of 3. You guys will actually touch the pi button, but pi over 2 plus I, and I'm going to show you guys, I'm pretty sure this is not going to work, over 2, close parentheses, and it gave it to us. This is called Euler's form. We'll look at this later, but we're just going to go menu, number, complex number tools, and we're going to convert to rectangular, which is turning it back the other direction. Hit enter. Oh, it lands right on let's see, the negative y, I guess you'd call that the imaginary dimension here, down here along this one. That's why there's no real part. So you would just say 0 plus 166.9 I. So it's pretty friendly. You just literally are plugging into your calculator here. If you needed to do more than that by hand, you would just do each component, multiplying it out, 3 times the cosine of this, plus 3 times the sine of this, but it's doing it for you, so I don't think it's necessary to break it out piece by piece. Only thing that we didn't really cover here, but we talked about in passing earlier, complex numbers, we use radians. We're just going to be consistent with that idea, using radians. Okay. We looked at some of these already, but really we're going to be using the modulus, we're going to be using the argument, we're going to be using that I button. And remember, you have to actually come down and click on the I button or else it won't work for you. You'll get a failing. And then you want to be using radian mode. Okay, so again, I wouldn't necessarily work on every single question in here. Some of these came from some electrical engineering homework. So here they're using J as an I. You might see that show up if you ever, if you choose to take electrical engineering classes, but they use J instead of I. Why? I don't know. They just do. Maybe to keep consistency between different variables or forms of things. I'm not sure, but use I when you're doing it. And then here, it's just practice plotting. So I think you probably should be okay here. And convert numbers from rectangular form to polar. That's the cis, the rCiS form. And then from cis form back to rectangular, or it's also referred to as Cartesian form. I don't know that you need to do every single one of these, but do some. do some for sure. And that should carry us through till next time.